Hello everyone, I'm Pen Jiang from Xi'an Jiaotong University. It is my great honor to introduce our work, Bidirectionally Densifying LSH sketches with empty bins. This is a joint work with Pinghui Wang, Junzhou Zhao, Shuo Zhang, Yiyan Qi, Yinghu, Chao Deng, and Xiaohong Guan.
Here are the contents. Locality-sensitive hashing, also referred to as LSH, is a special kind of hash functions. It hashes similar items into the same bucket with a higher probability than dissimilar items. They can be used in many applications. For example, data compression and similarity estimation, kernel methods acceleration, fast similarity search, and machine learning acceleration. A popular LSH method is BC parameterized LSH, which is used to search the input items that have high similarities with the query item. It can be divided into two phases, pre-processing phase and retrieving phase. During the pre-processing phase, it utilizes sketch methods such as min-hash to build LSH sketches of k-bins for each input item and the query item, respectively. Then, it stores our input items into big hash tables according to their sketches. During the retrieving phase, for the query item, it implements the same hash operations to probe big hash tables and obtain candidate items that are stored in the same bucket as the query item. Then, it performs exact similarity computations among all candidate items to detect similar items. However, when computing the LSH sketch, the above applications usually require to hash hundreds or even thousands of times for each input item, which is computationally expensive. Here we take the method min-hash as an example. Given two sites A and B, min-hash is designed to estimate the J-card similarity between them. Min-hash builds a sketch consisting of k-bins for each site, where each bin performs a permutation for all elements of the sites to obtain their corresponding hash values and only keeps the minimum value. Therefore, it needs large computational costs to build a min-hash sketch for each site. To reduce the time complexity of min-hash, OPH is developed by using just one hash function. It can be treated that OPH only performs one permutation and uniformly divides the space into k parts. Unfortunately, OPH sketch contains empty bins, which introduce large similarity estimation errors and hinder the application of LSH-based fast similarity search. This is because these empty bins cannot be ignored, and many dissimilar items belonging to the empty bins may be selected as candidates when searching similar items for a query. To address the above issue, some densification techniques are proposed to densify empty bins using the values of non-empty bins at random. Here, we list two classical densification methods, OPT-dense and fast-dense. OPT-dense backward densifies empty bins with values of non-empty bins selected at random in multiple runs until all empty bins have been reached. Fast-dense forward spreads values of non-empty bins into empty bins selected at random in multiple runs until all empty bins have been reached. Note that the site of non-empty bins does not change during the densification procedure, and the densification aims to obtain sketches that satisfy the LSH property. In other words, the probability that two values in the same position of two densified sketches is equal to their similarity method. But these two methods also face some challenges. First, both methods are computationally expensive for densifying some sketches. When the number of non-empty bins is near to 1, OPT dense requires OK time complexity for densification. When the number of empty bins is near to 1, fast dense requires OK time complexity for densification. Second, directly combining OPT dense and fast dense violates the densification principle. In this paper, we developed a novel densification method to solve the above challenges. Our contributions can be summarized as follows. First, we design reversible permutation functions, which enable us to consistently densify empty bins in either the forward or the backward directions. Second, based on our reversible permutation functions, we propose 3 densification strategies: forward spreading densification, backward computing densification, and backward trace densification. To densify a sketch, our method fully exploits the strengths of these strategies and smartly applies them in a joint manner. Finally, we extend our method to tasks, including similarity estimation, faster similarity search, and kernel linearization. The experimental results demonstrate that our method is up to 106 times faster than other methods while achieving the same or even better accuracy. The basic idea behind our method can be described as follows. We densify empty bins with non-empty bins using a family of functions h1 to hk or their inverse functions. When the sketch has a few non-empty bins, we can fast forward each non-empty bin to other empty bins by using functions h1 to hk. When the sketch has a few empty bins, we propose to backward determine the non-empty bins that will be replicated to each empty bin by using inverse functions of h1 to hk. The detailed computations of functions h1 to hk and their inverse functions are shown in the right frame. For each function hi, it maps integers from 1 to k minus 1 to integers from 1 to k, and it is used to randomly spread the ith non-empty bins value to other empty bins. The reversible permutation functions have 2 properties. First, the function hi1 to hik-1 is a permutation of integers in 1 to k except I. Second, based on the computation of functions, each function hij and its inverse function can be quickly computed. Therefore, based on the reversible permutation functions, we propose 3 densification strategies. The first strategy is called forward spreading densification. We use the parameter g to record the number of runs that have been performed. Then we enumerate each non-empty bin I in the set of non-empty bins in ascending order and compute hij to find empty bins of the sketch. The second strategy is called backward computing densification. For each empty bin z, we indeed densify it with the minimum values I and g, such that hij equals to z. The parameters I and g represent the index of an empty bin as the number of runs that have been performed. The third strategy is called backward trace densification. It is another way to achieve the same target for backward densification. Here, we use the site SZG to denote the set of non-empty bins that can densify its value to the empty bin z with j runs. For each empty bin z, we initialize j as 1 and enumerate each I in SZJ in ascending order to check whether it is non-empty or not. When encountering a non-empty bin at the jth round, we densify its value to the empty bin z. Based on the densification procedure of these three strategies, we can have their time complexity in the table. By comparing the time complexities of these three strategies, we have the following four cases. During the densification procedure, we can smartly choose one of these four cases for faster densification according to the number of empty and non-empty bins in the sketch. In our experiments, we use two kinds of datasets to evaluate the performance of our method: synthetic datasets and real-world datasets. For synthetic datasets, we randomly generate 10,000 vectors, each with k gamma empty bins. Here, k is the size of vectors, and gamma is the sparsity, the fraction of empty bins in the sketch. For real-world datasets, we use three kinds of datasets: binary datasets, weighted datasets, and image datasets. We compare our method with three baselines: OPT dense, fast dense, and a method OPT fast dense, which combines OPT dense and fast dense. When the number of empty bins is larger than the number of non-empty bins, OPT fast dense first implements fast dense and then uses OPT dense. Otherwise, directly utilizes OPT dense for densification. Also, we use three tasks for comparison: similarity estimation, similarity search, and kernel linearization. As for the densification time in the synthetic datasets, we measure the runtime of many sketches with different sizes and different fractions of empty bins. Our method is faster than other methods, especially when sparsity gamma is large. When gamma is large, it is easier to spread non-empty bins to empty bins, and thus OPT dense costs more densification time. In contrast, when gamma is small, fast dense costs more densification time. The densification time of OPT fast dense is between that of OPT dense and fast dense. We also measure the densification time of our methods in real-world datasets. Our method significantly reduces the runtime of other methods by more than 100 times. The sparsity of many real-world datasets is large. Therefore, the runtime of OPT dense is larger than fast dense and OPT fast dense, and the runtime of OPT fast dense is between that of OPT dense and fast dense. For the accuracy of our methods, we use the metric mean square error (MSE) to evaluate the accuracy of all methods in real-world datasets. Our method has almost the same estimation accuracy as OPT dense and fast dense for different sketch sizes in our datasets. Directly combining OPT dense and fast dense violates the densification principle, and thus the combined method generates large estimation errors. For the similarity search task, we randomly sample 10,000 items from each raw dataset as a set of query items, and average their retrieved candidates as well as recalls, where we set the parameter C as 3. As the sketch size increases, the points retrieved per query and the recall increase. Also, our method has similar estimation performance to OPT dense and fast dense, and is more accurate than OPT fast dense. Meanwhile, for the similarity search task, we also measure the runtime of our methods for building LSH hash tables, and we notice that our method significantly reduces the building time of other methods. Furthermore, we extend our densification method to kernel linearization. Here, we use SVM as a classifier to complete the classification task. And we use matrix accuracy and F1 score to evaluate the classification accuracy. And we measure the runtime during which we implement different methods to pre-process items before inputting them to the classifier. From the experimental results, we see that our method has a similar classification performance to OPT dense, fast dense, and the original methods in-hash and CWS, and is more accurate than OPT fast dense. Also, our method significantly reduces the runtime of building sketches, and its runtime is even smaller than that of training and predicting. In conclusion, in this paper, we first design reversible computation functions, which enable us to consistently densify empty bins in either the forward or the backward directions. Second, we propose three densification strategies: forward spreading densification, backward computing densification, and the backward trails densification. To densify a sketch, our method fully exploits the strengths of these strategies and smartly applies them in a joint manner. Finally, we extend our method to tasks including similarity estimation, fast similarity search, and kernel linearization. We notice our method is up to 106 times faster than fast dense and OPT dense, while achieving the same or even better accuracy. Thanks.